OChem 1, welcome back. Can you believe this? But this is going to be our last video for Unit 4 for new reactions. Oh shoot, I just realized that this is still called reductions from the last video. This should be called coupling reactions. I'm so excited. So you want to pause for a second. If you haven't watched the organometallics video, you need to watch that video first. I'm going through several of our metals in that video first. Now I want to apply those metals. So our pathways and some of our background and all of our Wikipedia links, all of our organic materials or organic portal or all of those links are on the organometallic video, and there's a whole lot of links on there and a whole lot of metals, so you definitely want to look at that one first. And I want to apply two reactions today, and both of those are coupling reactions. I'm so excited because now our synthesis is going to go through the roof. It's going to be so much fun. So even though this is our last video of new reactions, we're going to turn right around and do some problems in the next 2 weeks, practice tests, and a bunch of synthesis. So there'll still be some more videos, but they'll be of problems. We need to take all of these reactions in Unit 4 and apply them. So these are the last two. Let's kind of work our way through it, and I'd like to show you some of my shortcuts. Now remember, for organometallics, I'm not ever going to ask you the mechanism. That's going to be in a later class. I know y'all are chem majors now because you're fascinated. So you'll probably get those pathways in your inorganic class. And then in advanced organic class, you'll probably get some organometallics. So we're going to focus on applying our two coupling reactions. And the first one I'm going to tackle is the Gillman reaction. Remember the history of this one. This has been around for close to 100 years. Isn't that incredible? The idea of the Gillman reaction, the actual Gillman reaction, I believe, was in the 50s, the 60s. So take a look at that organometallics video. It's got all of the history. And what we learned in that video was that we can actually do something really special with lithium first. Now that reaction's been around for close to 100 years. It's the copper additive that came a little bit later, and that was given credit to Gillman. So our lithium can insert right there into our organometallics, can insert into our halogen bond. So we can do what's called a lithium halogen exchange here. That is that first step. Let's write that out, lithium halogen exchange. And then what's fascinating is then if you could react that as a nucleophile, it is a nucleophile. It's also a really good base. So if you were to mix that with an alkyl halide, what's going to happen, unfortunately, is you're going to do that E2 reaction. That's really not going to be a good SN2 nucleophile. So what Gillman did was throw in some copper, and that changed the whole dynamic of that reagent. So not just this, which we know would be drastically polar towards carbon. In fact, that would be an ionic bond between carbon and lithium. So throwing in that softer, bigger transition metal of copper actually made what's called the Gillman reagent out of that whole mixture. And it made those good coupling partners. So they are now really good partners. We're going to react these with an alkyl halide. Any kind of alkyl halide is going to work. Bromine is certainly the most common. Occasionally chlorine is used. And then we will see the Gillman reagents in OChem 1. We'll see those now in our coupling reactions. Those of you taking OChem 2, they will pop up again. They are very specific in 1,4 additions. In fact, they work very nicely for selectivity versus a Grignard will be a 1,2 and our Gillman will be a 1,4 addition. So they'll actually be in both semesters of OChem. You're going to see them twice. So now that we know how to make our Gillman reagent, let's use it. Our Gillman reagents, the super secret is that even though they have a 2 here, that's because of our oxidation state. And remember the organometallics video, that is our coordination of copper. So copper will add 2 of these alkyl halides. You're going to need 2 of these, but only 1 reacts. So only 1 gets transferred in our coupling. Okay. So it's a little sneaky with the 2, but I also want you to keep in mind that what gets transferred will be this whole group, but we're going to react on that carbon. So you'll see what I mean in a second. Let's take this and let's apply it. What are Gillman reagents good for? Well, what if I take simply a methyl bromide? This is going to pop up in your homework. Let's make it into a Gillman. So let's just follow that recipe. And now we're going to have a methyl group, even though we've got 2 of them on our copper, only 1 is going to react. And now this is a good coupling partner with any alkyl halide. So what if I take that Gillman and I mix it with our methyl bromide? Now this is what the definition of a coupling is. I'm literally about to react here and here and literally couple them together. So what happens is you now form ethane and you lose a whole lot of copper ligands and salts, and you are going to lose lithium bromide. You're going to lose a whole hot mess of stuff over here. I will never ask you that. I want to know what the organic product is. That's the one that we would isolate. And this organic product is these 2 carbons coupled together. So really, our Gillman looks complex at first when we look at it, but if you can remember, this carbon is where we're going to attach our copper, and wherever you attach copper is going to couple to wherever you have your alkyl halide. Now you can couple anything. So let's actually look at another one. What if we made a Gillman reagent out of our ethyl bromide? So let's make this Gillman reagent. We just made that in the last example. I'm going to just put a star right here on this carbon. And then we reacted it with an alkyl halide. I'm going to put a star right on that carbon. So what you do is literally couple them together. So this is going to end up where the bromine was, and we're about to couple them. So you keep your 5-membered ring, you keep this carbon, and now you attach the 2 carbons from your Gillman. So we just coupled right here. And let me add some numbers to that so that's pretty clear. So that would be our number 1 and number 2 carbon, number 1 and number 2 carbon. We just formed that bond right here is our coupling. So it's literally phenomenally handy, especially in alkane synthesis. You can start with an alkyl halide and generate your own Gillman, and then you can couple that with any other alkyl halide. So as long as you know how to make alkyl halides, you can couple them together. Really straightforward in synthesis. So let's try another one. Let's get used to just what those coupling partners are. Again, let's use our little super secret. Whatever your copper is attached to, that's going to be here. You're about to form a bond to your alkyl halide. That is right there. So let's take those 2 and couple them. I'm going to draw the ring. And I'm just going to turn it to its side. All right, let's couple to this carbon. And then I'm going to attach this whole chunk to that cyclohexane. So here is the bond we just made. And let's just let's double check me. Okay, there is 1, 2, 3, 4, 5. There is your coupling right here. You just literally stick those two carbons together. So I love the Gillman and synthesis. It will be possible, you'll see it in your homework, to literally start with methane and make all kinds of stuff. It's ridiculous what we're going to do with the Gillman. All right, so let's take a look at another one of our coupling. And that's our Grubbs catalyst, certainly more modern. The idea of coupling between two alkenes, or something called a metathesis reaction, has been around since the 60s and 70s. It's been around with other catalysts. It started with some thallium and some molybdenum, and I think even some tungsten catalysts to do this kind of chemistry. But what makes Grubbs modern and different is this is the original, this is the Grubbs catalyst number 1, but there are at least 2 or 3 generations, if not more, of the Grubbs catalyst. And it is shelf stable, which is phenomenally important because you can make it and send it to people, and you don't need a glove box. An awful lot of organometallics, you need a glove box. What makes Grubbs really stand out and really be the modern choice for organometallics for this type of reaction is that you do not need a glove box. Glove boxes can be quite expensive and cumbersome, and you've got to get trained to use them. So there are other catalysts that do this chemistry, but we're going to focus mostly on Grubbs catalyst. Now, I don't expect you to know the difference between the generations of the catalysts. Like I said, I have the original drawn here, but there are several iterations, and what's happening is you're keeping that ruthenium metal, but you're just changing some of those ligands. So a few of these ligands may have been swapped out for other ligands. So what Grubbs does is 2 different things that it's famous for. The first thing you can do with a Grubbs is literally couple or metathesize 2 olefins. Now they can be the same or they can be different. So let's color code our little R groups so we can color code what's happening there. And you can mix 2 alkenes or olefins, and you can couple them together. And what's phenomenal is that you keep the double bond. Now, what you have to keep in mind is that this is a true organometallic pathway. Ruthenium is doing a nice insertion and addition of those oxidative additions or insertions of those alkenes, and then it is rearranging and it is doing a reductive elimination of alkenes. But what happens is Le Chatelier principle, when it reductively eliminates this partner, which is ethylene gas, it is a gas, and this leaves your reaction mixture. So ruthenium can take on and add in those olefins, but the second it actually spits out this combination, you now lose this as a gas. And so the other 2 that are left behind are giving you this product, this metathesis product. So if you look at your starting materials, you are literally losing these 2 carbons. They are the carbons in your ethylene gas. So whenever you do any kind of metathesis with Grubbs, you have to have an extra carbon on both of your substrates because you're going to lose both of those as ethylene. So you will lose both of those as ethylene. So let's go ahead and color code and mark the carbons that get stuck together, and that is your inside carbons on your olefin. So when you use Grubbs catalyst, you have to make sure that you have what's called an exo double bond or terminal alkene. You need to have nothing but hydrogens on the ends of those alkenes. So I can't just take something like this and have that react with Grubbs. You have to make sure that you have a nice terminal. Then it works awesome. All right, so what Grubbs is also known for is something called a ring closing metathesis. So Grubbs is phenomenally useful in forming rings. So let's go through a little process. The inside carbons are the ones that are going to form that bond together. These outside carbons we're going to lose as ethylene. They end up here. And our Grubbs catalyst is phenomenally famous for its ring closing metathesis because now all kinds of ring sizes are available using Grubbs catalyst. In general, you rely on Mother Nature for Hoffman rules are called, and you make 5 and 6 membered rings preferentially. We can occasionally make a cyclopropane, which we saw with our carbene, but in general, and we saw with our Diels-Alder, we make only 6 membered rings. So with a Grubbs catalyst and our ring closing metathesis, then we can actually form all kinds of ring sizes. So what does that mean for you? That means, hang on, let me finish writing this, ring sizes. So if you see in your synthesis the cyclopropane, you're going to use your carbene. If you see your cyclohexene, you're going to use your Diels-Alder. If you see any other ring size, you're going to need Grubbs. Grubbs catalyst is the only way we've learned now to make any other ring size. So if you want to make a cyclopentene, you have to use Grubbs catalyst in order to do that. You cannot use a Diels-Alder or a carbene to make that ring size. So it's pretty awesome. Let's practice one of them. Let's just put a bunch of crap on some double bonds and see what kind of product we make. So let's just kind of link together something like this. And then let's take something like this. And I don't know, I'm just adding a bunch of stuff to it. And let's treat that with Grubbs. And let's see what we make. All right, let's follow our process. The inside carbons are the ones that are going to couple or metathesize together, and then these outside carbons are going to leave as ethanol. So what are we about to make? Well, let's draw it kind of funny. I'm going to just keep the ring right there. I'm going to keep the double bond. Only the difference is I'm going to add that chain like that. All right, let's count. 1, 2, 3, 4. 1, 2, 3, 4. And then here's the carbons we just coupled together. And then our byproduct would be that ethylene gas. That's going to bubble out of solution. So Grubbs is phenomenally useful. Look at how complex this is and just wait for it. Don't you feel like after what we've learned, we could actually make both of those partners? Heck yeah. So you know where we're headed. Grubbs and Gillman will be all over our synthesis questions. Remember, I won't ask you a mechanism. That's not fair. I've never given you the mechanism, but I will ask you to apply these in synthesis. And they're super fun if you remember our little tricks for how to apply those in synthesis. All right, so this is the end of Unit 4, New Reactions.